Hello everyone, I'm Hanyeoreum from KAIST, and today I'm going to talk about our work, which is Empirical Guide to Use of Persistent Memory for Large-Scale in-memory graph analysis. In this presentation, I'll briefly introduce two of our observations, which are opposite to the general expectation. So let's start with a simple question. Suppose that you have to learn a graph application and the size of the low graph file is 100 gigabytes. Then how much RAM would be enough to perform it efficiently? Some of you may think that 128 gigabytes or 256 gigabytes would be enough since it is larger than the graph size. However, based on our observation, the answer is none of them is sufficient. Here is the data that shows the memory footprint while running a graph application. We found that during the graph construction phase, memory requirement becomes 6.71 times greater than what the original graph requires. Also, in the algorithm execution phase, the final graph data requires memory space, which is 3.93 times larger than the original data. So here is our first observation. The runtime memory requirement is much higher than what we expect. If there is not enough memory space to contain this runtime data, the system might fail because of out of memory. Although we extend the memory by combining it with the underlying storage, we will experience a serious swap overhead. This graph shows that the amount of data to swap and execution time both sharply increase when we process a large graph, which has more than 8 billion edges. Therefore, we need to increase the size of system memory. To this end, we can utilize large-sized non-volatile memory, such as Intel-obtained PMEM. It is much denser than conventional DRAM and could be configured in app direct mode and memory mode. If users configure PMEM in the app direct mode, it separates the address space of local DRAM and PMEM. So PMEM configured in the app direct mode provides storage-like data persistence. When a user application runs in the app direct mode PMEM, it is required to utilize either the conventional storage stack or PMEM-optimized system software. The state-of-the-art techniques are converged into DACs, which removes most software interventions imposed by the storage stack. However, DACs also exhibits 3.7 times slower performance than DRAM due to the long latency of the PMEM device. When PMEM is configured with the memory mode, the local DRAM is utilized as a memory cache for PMEM. Therefore, it can provide DRAM-like performance, but does not guarantee data persistence. Thus, to make data persistent, we should flush it to the underlying storage, and the overhead is significant as shown here. We tried to figure out the best PMEM configuration for large-scale graph processing. Based on our observations, it should maximize the performance in memory graph systems while minimizing the overhead imposed by their persistence control. And in this work, we focus it on the benefits of the conventional storage stack instead of using the current solutions. Since this page cache naturally reaps the benefits of DRAM caching, it can take performance benefits that PMEM in the memory mode enjoys. In addition, the legacy file system guarantees ACID properties in a natural way. Thus, it can minimize the overhead brought by the hand-worked persistence control management. So we modified a representative in-memory graph framework, Ligra, to make it utilize the merits of the storage stack. To this end, we configured PMEM in the app direct mode and low mode namespace. Then we replaced the DRAM space of the heap with the PMEM and made Ligra to access it by using the library called LivePMEM. We compared the in-memory graph processing performance among 4 different configurations, and as a result, we found that PMEM using the storage stack shows the best performance, since it utilizes DRAM caching while minimizing the persistence control overhead. So here is our second observation. Storage stack could be the best solution. In conclusion, we conducted a comprehensive evaluation with the real PMEM devices. And we modified Ligra to utilize the benefits of the storage stack and found that it outperforms the others. Since there is a time limit, I've introduced only 2 observations in this presentation, but there are much more points that we observed. So please refer to the paper if you're interested in this topic. Thanks for your listening.